सर आवाज नहीं आ रही आपकी। माइक म्यूट हो गया आपका।
or I don't know what is happening. Okay, okay, fine. Okay, so I was just telling this is take this as an opportunity and learn something, experience something, and understand the importance of circuit design. Okay, and the thing is, requirement is you have to do something, select some circuit, do some effort, and understand how the circuit works, simulate it if possible, and try to breadboard it. What is breadboarding it? Breadboarding is given an image of breadboard. I think yeah, this is called breadboarding. So this circuit is kept on a board. Okay, so this is a virtual connection. Although it's not virtual, you can say there is temporary connection. This is temporary. You can fix all those things in the breadboard and test your circuit whether the circuit is working fine or not. Okay, so this breadboard has a lot of pins, which are some are internally shorted, some are not shorted, and you can keep your different devices and connect, simulate. Not simulate. You can just see whether the test the circuit whether it is working properly or not. Okay, once it is working properly, then you can come back to the fabrication. You can take a small PCB and uh, use a soldering iron and use solder and just a metal connection and just connect this through conductors all those circuit and you'll fix it. Okay, then after this it will be very robust and very reliable and you can because it depends upon this soldering. Okay, so it is very simple. I will explain you how to solder and although it may be available in internet also. Okay, if this is not possible, you're telling I cannot buy any hardware, I cannot fabricate, I cannot solder, I don't know anything, I will not go outside, so then also don't worry. If someone is like this, then you have to go for simulation. Yeah, then you go for simulation. Okay, okay, you have to take a small circuit, you go for some simulation. Okay, if that is also not possible, someone say I cannot simulate, I don't have internet, I don't have any tool, I don't have system, so no problem. Still I am giving you opportunity. I mean, you can have a write a select a circuit from the internet or from any textbooks, then to understand how the circuit is working. Okay, explain the how the circuit works, what is the application of the circuit. Okay, and how can you modify if possible, if not also not modifying is also okay. Whatever you explain the circuit, how the each components work. Okay, that's it, and you can submit that also as a scan copy. That is also option. Okay, I'm giving some project suggestions, like if you have some common very famous circuits which already out there, which already design is also out there. You can also select, you can design also if you want. The clap switch and automatic street light, this is very simple. We need one light sensor to detect whether it is night or daytime. If it is night, the light has to be on. If it is daytime, light has to be off. That is automatic street light. That is electronic letterbox. Very simple. When something is inside the uh, some letters are inside the box, there is a light on so that you can open it. Okay, there is some letter coming or letter is there, so they can open it. So this is simple techniques, small simple sensors like tactile sensor, something this is also available, or you can even simulate it, not a problem. So these things, and some are rain alarm. This is uh, when there's a rain, just detects. Today I will explain small example of that. Okay, heat sensor. Okay, you can put a heat thermistor or some a lot of options, a lot of things available in low cost, and fan controller. Uh, temperature based on this in temperature sensor only. There is a motor, small motor controlled by a small 9-volt battery. That's it. If the temperature sensor is high, that means the fan has to turn on. That's it. And this level can go to higher to lower, so it's up to your interest. If you can take a simple thing, submit, or you can go for something challenging thing and you can try. I don't tell you we want perfect output, but everyone should try. That's it. That's the only thing. I should have everyone should have their own experience. Yes, I did. I tried this. I faced this problem. I tried to solve this thing, etc., etc. Okay, fine. So you can, this is some sample circuit I'm giving. This is something you will get from the internet and some books. Okay, there are some books like electronic circuit for you, circuit electronics for you.com. and circuit today. A lot of magazines are there, a lot of internet websites also explain a lot of things. Okay, and documentation. You have to write something on your own hand. Whatever you have tried, whatever you have experienced, whatever is your ideas, whatever you have gained uh, happiness or whatever challenging, whatever distress, whatever you felt, you have to write a documentation. About technical, it should be technical. It's not like it is like a novel. It should be technical to explain all those things. Okay, and once you submit, I will ask you something. If you submit, sir, I have done this, then you submit this handwritten. I'll ask, okay, what is your experience? How did you do it? What is the circuit working? Okay, so at least you should make sure that you know the working of at least one simple circuit. Okay, completely, so that you know how each of these components within the circuit works and what are the applications, etc. Okay, so I have send you this in the classroom, Google Classroom, and I will send you if you want the WhatsApp also. But only thing is, take it seriously, sincerely, so that you will have something, a good experience, and that's it. I know a lot of students will be willing if all the uh, previous classes which have given them some projects. There are some students who are really interested, who are waiting for them, they will do it. And that is only I want. I don't want I know that everyone will not be interested. There will be few only interested for this. But this is for them. But the others also should try something so that they also in the future, they should know how to approach a project, how to complete a project. Ultimately, in the industry, what they're looking is your this kind of project experience, what have you done. It's not what no companies ask what you have learned, what the theory you have learned, how many mm, equations and how many these things you have learned. They will ask what you have done, what is your this experience. That is what matters. And you cannot bluff there. You have to, if your experience, if you have done it, it will show through your words and you can feel it. Okay, so try it. You have a lot of options. You can go for manufacture PCB, uh, PCB soldering, or you can do a breadboarding, or you can do simulation, or even nothing is there. You can just study a circuit and explain how it works, etc. That's it. Okay, fine. So we will continue with our topic. So this time I will give you some assignments, whatever transistor problems we have discussed, and we'll have a test next. I think we can have a test next week, maybe Wednesday. Is it okay? Can anyone tell me? Is it okay? So we'll decide the end of the lecture. Maybe next it can be Wednesday. Oh, sorry, not Wednesday. Sorry, Thursday, Friday, Saturday. Any of the days we can keep our text, not text test. Okay. So yesterday we discussed. Um, yeah, yesterday we discussed the operating point. Now today we'll discuss why the operating point is very important. Okay, we discussed operating point is also called Q point. Okay, operating point is also called operating point is in a lot of tests we will find this point Q point, very important theoretically. Q point. Okay, operating point is a Q point. So what does operating point gives you? Operating point gives you the specific voltage and current uh, over which your input is sliding. So that this is the concept I'll discuss today. What is the relationship with AC input and the Q point? Okay, right now we have tried the operating point of a transistor. We know what is the current and voltage of the transistor, VCE and IC of a transistor. That is called the Q point, which is fixed on. Okay, that is a DC point, which is fixed. We are fixing the operating point. That is nothing but Q point. So today we'll discuss why we need to fix the Q point and how we will fix the Q point. That's very important. Now, once you understood why it's so important to fix the Q point or operating point, then only I can fully explain or make you understand the importance of biasing. Okay, so biasing plays a very important point in fixing the voltages and currents of a transistor. Okay, that's ultimately fixing the operating point of a transistor. There's nothing but the Q point of a transistor. Okay, so today I'll try to explain uh, why is it important for fixing Q point. So yesterday I'll just refresh yesterday's concept. So we have learned any circuit based on the circuit characteristics, I can draw a plot I versus V Kara, I can have a straight line. Now, this straight line touches 2 points. One is maximum current point, I max, and 0 or minimum voltage, 0 point. Another point is maximum voltage point and minimum current point. That is minimum current point is 0. Okay. So when I plot a line between I axis and V axis, I'll get different operating point, different points in the line, which all can be a possible operating point of the device. Now this plot is I'm getting or I'm procuring from the circuit characteristic. That is the voltage, maximum voltage possible. That will be here. You should know that maximum voltage is always this point, and that definitely will be VCC of your circuit or the input voltage VCC. Okay, and I'll also get a maximum current at one point, and that will be the, for example, VCC divided by RC, the current, maximum current will be VCC divided by RL or something, maximum possible current of that point. But at that point, my voltage will be 0. That means my device is short circuited at the top point and device is open circuited at the bottom point where full voltage is applied across my device. Okay, now over this characteristics, over this load line, what I'll do, I'll plot my device characteristics. Okay, so what happens if it's a diode? I can plot it over the diode characteristics over my load line. So what I'll get something like this. So if I plot this diode Kara, now this intersecting point, which is called the Q point or operating point. So this is the operating point. Okay, so how you get the values? This is the V corresponding to that. So there is a V voltage corresponding to that point. This is called V operating. I call V dash, and there's a corresponding current also in the I axis I dash. So this is the I dash and V dash operating point of that device in that particular circuit. Okay. Now, if I change my diode, I put a new diode for a new company. Okay. So the new company diode gives a data sheet have a transistor characteristics or diode characteristics. It is something like this. So again, I plot this also again in the load line. So I'll get another crossing point. So this is the new operating point of my circuit. This is V double dash and the current is I double dash. Okay. Like so on and so forth, I can go on putting new device characteristics on this load line and I can get the operating point. Okay. Now what if it's a transistor? Okay. So the transistor, I already discussed transistor, we are interested in which point? Operating point, that is a collector point, collector current, collector emitter voltage, VCE and IC. Okay, so if it is a transistor, then operating point will be the output characteristics of transistor, that is VCE versus IC, something like this. Okay, I think you will be familiar with already something. So this have different points of a this is one transistor I'm plotting only, and one transistor only have different output characteristics based on IB, right? So IC is a function of IB. So IB, based on IB, I have different operating points. This is for IB one, and this is for IB n or n whatever. Okay. So based on my IB, I can vary my different operating points. You can see all these are the possible operating points and all. Okay. Okay. So this is for the transistor. Now, I want to ask you one thing. Initially, we have drawn the diode circuit like this. We have a resistance, load resistance, and we have an input voltage, say VCC or V in, VI. This is RL. Okay, so initially my load line was like this. Okay, if I say the load line, not directly load line here, it will be like this. What are the 2 points? This point is VI, maximum voltage across my diode, Okay, that happens when the diode is short open circuited. So zero current flow. So Vi zero is the bottom point. What is the maximum possible current possible? Vi divided by R, maximum possible current, and that which voltage will be zero voltage, right? When the diode is short circuited, that means there's no resistance at that the terminal point. So with the terminals at T1, T1, T2. This is a terminal where I keep my device, which can be any device, can be any company diode or any manufacturing, any device. So these are the different points where my now suppose suppose I want to change the slope of my load line. So I'll ask you this question. Suppose I want to change the operating point. I want to increase or improve the operating point. Some, for example, if I want to change the operating point to this new operating point, both I'm increasing the voltage as well as current of different points of the load line. So what should I do? So you can see this load line is a function of a circuit. So I need to do something change in my circuit to get the new load line. That means I'm going to shift from this load line to this load line. So what is the change I should do to get the new load line? There are two things here. One is device here. Device I cannot touch. Device is a device care. I don't need to. I don't have any control over load line. The device because device gives me device cara which I plot on the load line to get the operating point. So here the two parameters to vary. One is Vi and there is R. So you can see this happens if I increase the VI. VI if I increase a new value, you can see the current maximum current also increases. Maximum current at the low voltage also increases as well as maximum voltage that is open circuit voltage also increases. So my load line is parallelly shifted to the top with more voltage and more current in the operating point. Okay. So as I increase my VI or VCC, my load line is shifting upper and upper. So again, if I want to shift again, I'll again increase the VI to maximum value. Again, I'm shifting my operating point, and so on and so forth. I can increase to any any area in this line. Why? Just increasing the physics. So as I increase my voltage input or in source voltage of my circuit, my load line is parallelly connecting all those voltage and current ordered pairs, which is higher than the previous load line values. Now, this is one option. I'm just increasing VA parallelly, I can increase the load line. So what if I want a uh, new load line where current maximum is only increasing, voltage maximum is same. So what I'm saying is I want a load line like this, the new load line. So what should I do? Yes, yes, very early. Except is decrease the resistance. You can see how you got the answer. Yes, you noted one thing. The voltage maximum doesn't change. Voltage maximum didn't change at all. That means I don't need to touch the voltage. So what is the other thing? Yes, RL. So here you can see the current has been increased, right? The current and when the voltage is zero, that means diode is short circuited. Still, my current is increased. The current is increasing only when the RL is going to decrease, right? So what I done? I decrease the value of RL. So my load line going to shift. That means giving stand is slope is becoming higher because slope is higher when resistance is becoming lower and lower and lower. Okay, getting? So this is happening. This is happening when my resistance is becoming smaller. So what happens if resistance is becoming higher? What happens? Yes, opposite happens. Your load line will become having less slope like this. The green color indicates my load line is changing as my resistance is increasing. Okay, that's it. So this is just you should have a visual understanding of operating point, and I'll also explain. in a practical scenario, why the operating point is important. Okay, so these two concepts we should understand: operating point, how the change in voltage affect the load line, how the change in resistance affect the load line. This is common for the transistor also, transistor output circuit. Okay, so what I mean by transistor output circuit, you already know transistor. Here we are discussing the two circuits. One is this is my output circuit. There's some voltage here and the current here. This circuit is the most important for design because here we are concerned about the IC and VCE of a transistor. That is nothing but output carrier. So this is the point where we take the amplified voltage. Okay, so this is my output portion of the transistor. So this is my output carrier. So always I'm concerned about this voltage and current. And what is the input? Input I have a base voltage and base resistance. Okay, so this is the input characteristics. Okay. So input characteristics are IB versus IB transistor IB versus VBE. So this is VBB and this is VBE. Okay. So this is blue is input and red is output. So we are concerned about the output carrier, that is IC versus VCE, etc. etc. So the load line especially we draw based on the IC and VCE in transistor. Okay. Now let's see how the load line is affecting your how load line is affecting your input and output characteristics. Okay. Now before that, I will introduce another concept. Now I'm plotting. This is VBE, input characteristics. VBE versus IB. So this should be IB, base current IB. So I think you should know that what is the output coming. This is something like initially there is a diode is off, base diode is off, then it becomes exponentially increases, something like this. Okay, fine. Now, if VB controls the IB, that means IB is a function of, you can write like this: IB equal to a function of VBE. Okay, right? Similarly, you can write what? IC is a function of IB, right? So that means what? You can see that IC definitely is a function of IB, VBE. Getting? Nothing. I'm just not telling you a new fact. It's a simple thing. IC is beta times IB. What is IB controlled by? IB is controlled by VB, input voltage. So definitely IC is indirectly controlled by the input voltage, right? So IB is a function of VB, IC is a function of IB, so IC is a function of VB. Okay. So the same graph, what I can say, the same graph, I can tell that VB always controls my IC because IC is definitely is function of IB in the active region at least. Okay, so I can say I can draw the same graph with IC also. Okay, so I can draw here. I can say like this that here I can plot my IC also. Although the scale will be much different, but still I can, instead of IB I can draw the IB also. Okay. Now till now we have discussed the DC points. So if I draw the IC also, how the graph looks like, exactly same. There's no difference. So I'm changing the graph like this. This is VBE, and IC. I see. So the graph what is the graph here? Same, exactly same. I'll get exactly same. Something like this. Okay, exactly same. Now, uh, now there is a one very fundamental thing I want to explain here. Very, very, very fundamental thing. Very fundamental thing. So this is the basis of the amplification, right? So here you can see, is it audible? I'm audible, right? I think everyone should be very attentive here because this is the root concept of amplification. If you understand this, you understand how the transfer is amplifying, how the gain of beta and all those is coming. Okay, so here I am showing the two values, which are the IC collector current and base emitter voltage VBE. If it is not clear, I'll just write nicely. VB, this is VB. Okay, VB. Now, now, uh, say I'm putting all my biasing at DC, everything fixed. My biasing means DC operating point, everything is fixed, right? Now, you can see here, if I consider VB as an input, if I consider VB as an input, what I mean is, if I consider VB is the controlling parameter of the current IC or IB, whatever, both the same, but IB is controlling IC. We are concerned about IC because output I'm concerned about IC only because that is my current in the output. Okay, so VB is controlling the IC. Now, how VB is controlling IC? As VB changes, IC is also changed. But the question is, what is the relationship between the change in IC and the change in VB? So, based on this graph, I'll just small. Initially, my operating point was this thing. I'll fix a VB. Its operating point was this point. Okay. The operating point, if I show you, this can be written by a red thing. This is my operating point. This cross operating point. Okay, so that VB I'll fix, that VBE I'll fix. So this is my operating point VBE. I fix this. Okay, this is my operating point. Correspondingly, I'll get another operating point in current, the current IC operating point, IC dash VC dash whatever. Okay, so this is the operating point. Now, now let's see. Now let's see if I slightly wiggle VB. What is wiggling? What is I'll tweaking? Tweaking means slightly I'm varying the voltage of VBE. Although I'm told you this is biasing, we are not talking about AC till now. We are only talking about the DC biasing, fixing the DC voltage. So, but right now I'm talking. If I vary the voltage of VB slightly, what I mean by that? Slightly I wiggle. Wiggle means I slightly make it to and forth, slightly up and down from the mean position of the operating point. Either other method of maybe small half a millivolt or sorry few millivolts, 10 to 20 millivolts as wiggle it. DC, we are talking about DC only. So just to understand how much is the output variation IC, I'll just again plot it again. I'll just from this point I'll straight line again to the. So when I VB slightly shifts, you can see IC also slightly shifted. Now what is the how much IC shifting? You go straight line. So this is IC dash 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 coming down, and VB slightly shifted. IC has come down. Now if VB has increased, I'll plot it in different color. Maybe I'll use red. Okay. So when VB slightly increase, what happens? Again, I plot this to the our Kara. I get another point here, and corresponding current I'll get. I get a corresponding current here. Okay. So this, for example, IC dash. You can say I call it IC, IC triple dash or something. IC triple dash dash dash. Okay. Now what you're able to see? My slide changing the VB in the minus in the reduced VB as well as increased VB, or slightly positive reduction or negative reduction, is going to shift my IC greatly or dramatically. Okay, so how can I? So are you able to see this? For example, mathematically, I can say, what is my shift in my VB? This difference delta. This is delta plus delta minus delta. Okay, if I shifted VB plus delta, what is shift in my VC? Sorry, IC. I'll see that it is a bigger shift. What is the shift? It is a bigger shift in the top direction. Bigger shift. I call bigger. I can say bigger delta D, bigger D. And if I reduce my VB, I can see a bigger reduction in my IC, reducing much bigger correction. So what is happening? There is mismatch. There's a difference between the change in VBE and the change in IC which I'm observing. Even if slight changing in VBE is observed, I can change a dramatic change in my IC in the output part. Now this ratio of my change in input voltage VB to the output current IC is called transconductance. Transconductance. It's called GM. What is the name of this concept? This gain or this ratio is called trans. Trans means input and output. It's like a trans means it is a relation between input and output or output and input. Transconductance and there is transconductance. Conductance. What is conductance? Theory आपने पढ़ा होगा. What is conductance? Conductance is one way resistance, right? What is resistance? Resistance is the opposing of the current, opposing the ability to oppose current called resistance. So what is opposite of resistance? The ability to allow the current to pass through. That is one by resistance. That is called nothing but conductance. So this property is called transconductance because there is a relation between the current IC, change in current IC divided by, so I call delta IC divided by delta VBE, delta VBE. Getting? So this number is called transconductance. Getting? So this is one of the main parameter which shows you how much change in the output voltage, output current you are getting by slightly giving a small change in the input. Okay, I think this concept has to be understood. uh, so how this is possible? Because of the slope. You can see the slope of your curve. The slope of your voltage versus current curve is allowing you for a dramatic change in my IC, even if a small change in VC or VB, sorry, small change in VB is given. Okay, here the small change in VB on up and down is causing a dramatic change in my IC direction. Great change my IC is possible. Now we can see, so let's explain this transconductance. Transconductance is the ratio between the IC, change in IC divided by change in input voltage, change in VB, base voltage. Okay, that's called transconductance. A small AC signal, so this change in VB we can consider as a small AC signal. Ready? A small AC signal VB is superimposed on the DC. So which point? Superimposed on the Q point. Superimposed on the Q point is called VBE. It gives rise to a it gives rise to a collector signal IC. Okay, and that IC will be a big value compared to the change in that change in IC is comparatively big than the change in VBE. Okay, and this ratio is called transconductance, and it is represented by a letter GM. Transconductance is represented by G, small letter GM. Transconductance GM. Okay, so I'll draw one more simple diagram of the same thing, but in a different way. I can show you this. This is your and now I'm plotting. This is IC versus VBE. IC versus VBE. and the plot is like this. Okay, now I'll fix my DC operating point. So I call this is my operating point. So it's a DC. So I have capital V, capital B, capital E, VB. And what IC I'll get? I'll get IC as the Q point. IC. So this is say for example VB dash. So IC dash is my operating point. Now, now I'm wiggling VB. Wiggling VB means what is the actual meaning of wiggling? Wiggling means I'm giving a small fluctuation in my DC operating point. So how that fluctuation will be coming? That fluctuation will come when you give superimpose a small AC over your DC operating point or input point. That means I'm putting a small AC voltage over my DC VBE. So what is happening? So what is the meaning of that? That means I'm giving a small AC. I can draw the variation AC in the bottom, like the small AC I'm giving here. You can see I'm giving a small AC VB. So that AC I can represent Y V, small letter B, small letter V, small letter B, small letter E. Like we already discussed, AC and DC notation we have discussed. So we are giving a small VB AC voltage, okay, it is fluctuating my VB slightly lower and slightly upward. This is fluctuation in my VB happening because of a small AC voltage applied in the base circuit. Now corresponding to this fluctuation in my VB, what you can observe that I'll get a big variation in my IC. So how you can draw that thing? You can see this point like this point like this. Okay. So what is the change I'm getting? Corresponding to each of this point of my input waveform, I'll now plot the input waveform over this thing. I can, if I plot it, so corresponding to each point of my DC AC, I'll get one point here. So I can exactly draw the whatever input voltage I am given, I can exactly draw here. So you can see if you plot it, what the change of IC is getting, you can get this is the maximum point, this is my minimum point from with respect to input. Okay. Now if I map each of my input to my output, I will get exactly a sine wave with respect to the input, something like this. You're getting? Although here this is exactly not right because frequency is changing. So frequency is also remain same. The frequency obviously should not change. So this will be something like this. Why this variation is coming? Because my VB is also fluctuating because of the input signal. Okay. So even a small input signal or small fluctuation in my VBE is producing a massive fluctuation in my IC. No, not only IC. If I give a more resistance in the output, say for example, although I'm getting a better IC, much greater IC, not only because of beta, but because, yeah, one thing is because of beta variation. Another is if I put a higher resistance in the output path, this higher current into a higher resistance, I'll get a much amplified voltage, much amplification in the output voltage. Because ultimately, voltage output equal to IC into VC. I can say the transistor power dissipation. IC into VC. So here the IC is the, so I already got the IC, a bigger IC, and this bigger IC will be multiplied with a bigger load resistance into RL, bigger load resistance to give me a bigger output power or voltage, output voltage in the output circuit. Okay, so what we have discussed? We have discussed although we are biasing, this biasing over this biasing or over this operating point, I am slightly changing my input voltage VB. That is actually, in reality, it is giving a small AC signal over my input input circuit, that is base circuit. So a small wiggle, a small change, or small AC in the input circuit will give me a dramatic great variation in IC in the output circuit because of the beta. Okay, so the DC gain of the transistor. And this current, if I multiply it with a bigger resistance, I'll get a greater voltage because V equal to IC into RL, I into R. So I get a bigger voltage in my output circuit. Okay, so this is the fundamental secret of amplification which we see in a transistor. Okay, so DC operating point is very important because now if operating point, now we will see what happens if operating point is not designed properly or not kept properly. Okay, now I'll draw the output characteristic. So we are now the transfer as output characteristic, something like this. Okay, so now I'm plotting IC versus VC. Now we have the load line. I also draw the load line. So different operating points are possible here. I call this as a Q point 1, Q1, this is Q2, this is Q3, and so forth. A lot of Q points are possible. Q4. Okay. Now you can see we already discussed how the Q point uh, is the midpoint where my AC wiggling is AC wiggling for example there is a 0 point for the AC, that is my Q point. Reference point for my AC is the Q point. From that Q point, if I increase my slightly the voltage input or base voltage VBE, I'll get a greater variation in the collector. So my input AC will be taking Q point as a reference or a zero voltage. Okay. Now, if I take the Q point here in the Q1, if I take Q point here in the Q1, what happens? You can see, you can see, uh, there is a problem here. Why? Because your maximum current is IC. Okay, so if I slightly vary the Q point, what happens? This is your Q point here. This is the reference voltage for your AC typical slow. So if I vary my slightly vary my input voltage to a reverse negative side, what happens? You can see that the operating point is going to slightly shift. The current curve, the curve you can see here is going to come down. The curve is something like this. That means this is not a proper point because your output IC, the gain beta is going to reduce here because the IC is coming at this point. That means we are not operating the active region. Now this point is called saturation region. This point can see as VB is reducing, your IB is also going to come down because your amplification is not proper here. And further increasing VB also there's another problem here. You can see here the ideally your output should be coming like this. But here you can see this I will not be coming in the output because IC maximum is this is IC maximum. So what is the problem here? My output is expected output should be showing much greater current than my maximum current IC possible. Maximum current IC possible is the load line, top of the load line. But when I put my Q point at this edge of my load line, what happens? My current will be clipped. That means clipping means I will not be able to show this top portions of my current. Why? Because my operating point has been kept in a border of the load line or a nearer to the saturation point. This point is called although I have not explained saturation, so I will explain saturation. This is saturation region of a transistor. Saturation region of transistor when there is a tremendous increase in current with respect to voltage. That means transistor is on, but we are not able to. It's like dramatic slope. The relationship between IC and VCE or IB and VB is very high, very large. Okay, so right now, based on this graph, what you can understand, while keeping a Q point nearer to the maximum IC or minimum VB, there's a chance that your output voltage may not be fully, what we can say, cannot be fully visible in the output. It gets clipped. You can see here IC has a maximum value here, but your expected IC should be, it has to be shown much value, much higher value in the output. But because your IC maximum value is decided by the maximum operating voltage and resistance, etc., your output voltage or output voltage will not be able to show the maximum points, because obviously your maximum Imax is already this 5 ampere, 5 milliampere, but the amplification required will be showing you 6 to 7 milliampere. Then definitely that part of the signal will be, definitely it will be clipped. We call it clip. Similar problem happens in the bottom side also. In the bottom side, when there is slide, you can see this slide transmission cutoff. At this, if I operate at this point, your Q point, if I operate the Q point here, you can say Q point, Q.7. So I operate at this point, what happens? This point, you can see, what you can see? You can see this current, the current IC, you can see there is, current is very negligible here. You can see current corresponding to the Q point, the current is practically zero. So what happens? You will not be able to represent the lower current. All this lower current will be clipped. All this lower part of your output waveform or output signal will be clipped. Your loss of signal happens. Lot of noise. That means clipping, distortion happens in your output. Why? Because we put the Q point in the nearer to cutoff region. Nearer to cutoff region. Earlier we put it nearer to saturation region. Now we put the Q point nearer to cutoff region. So we'll again lose lot of signals, because the variation in IC in the left side is not permitted. So transistor should not be coming into cutoff region, nor it should be entering into saturation region while it is supposed to amplify the signal. So ideally, you can see, to get the maximum wiggling of the output waveform is possible when I keep a Q point at the point Q3. Here the Q3. If I give a Q3, I can see I can have a maximum possible wiggling. How? Because if my input is varying this much, you can see your output be varying somewhat like this. This is your reference voltage. You can see this corresponding. You can get a full. You can see the full waveform in the output. Okay. Here I am showing IC versus. Sorry, this is not VB. It should VC. This should be VC. Okay. So based on my variation in the VB, I should be able to show the full voltage waveform in the output. So I should put my Q point in the middle of the load line ideally. Should not be near cutoff, nor should be near saturation point. Okay. So this concept at least you should understand what, how to, where to fix the Q point and where to not to fix the Q point, and what is the importance of Q point. And if Q point is not fixed, your output will not be fully visible, or it will be clipped, it will be distorted. Okay, because the signals need lot of what we call bandwidth. We lot of voltage variations called voltage levels, different levels. So, for example, if you have a different, it's not bandwidth. Bandwidth is actually frequency. Sorry, it's not the voltage bandwidth. It is the voltage leveling. That is, if you have a given a wiggling freedom of 1 volt to 4 volt, that is 4 minus 1, 3 volt, you can vary the output. For example, else you are getting only 1 volt wiggling, at least 3 to 4 volt, it is restricted. The signal output is still restricted. Okay, so if you fix the Q point ideally in the best point, then your output amplification, output signal have maximum peak to peak voltage. It can represent fully the amplified output or amplified input in its output. Okay, I think this concept fully is important. And right now we'll try different circuits. We'll understand different circuits to fix the Q point. Okay, so I think if any, is there any quick questions? I can take some questions right now. Else you go through your Google Classroom. I'll be sending the assignment in your WhatsApp also. I'll tell students to share it, and I'll also give some questions for the circuit part in practice, and so that next week we can have a test, maybe any day as per your. Okay, you tell me the date after discussing, and I'll fix next week. So we'll stop it here, and you can put your roll number.